Welcome to Rubber Duck Engineering. Tonight, we're going on a tour of Fuchsia, Google's new operating system. Yay! Throw the confetti! Anyways, it's going to be great. Come along for the ride. So, hi, Adam.
Hi, Eric. How are you?
I am pretty pumped because, we were doing practice pre-show for this, yesterday, tech checks and all that. And I just don't know nearly enough about Fuchsia, and I am excited to learn tonight.
You're asking lots of great questions. I hope you save some of the questions for the actual show.
We'll try.
So I want to set some context here. So I've been working on Fuchsia for about 5.5 or 6 years.
Mm-hmm.
And it's for that whole period of time, or almost all of it, it's been open source. But it's sort of been open source in this very low-key way where we do our code reviews, we publish our source, but we haven't really talked a lot about it. And one of the nice things about finally getting to the point where we've shipped the operating system on a consumer device is now we're able to talk about it more. We're able to engage with the community, and be able to have more participation in the open source project. So this is part of that. It's hello, how are you? Well, welcome to a tour.
Yeah, I think it's a good reminder. 5.5 years, right? And a non-zero, a non-trivial number of people. It just takes a long time to build big pieces of software.
I mean, especially this kind of thing feels like a camping trip. You only really have with you the things that you've built. And so, I don't know, when you go on a camping trip, right, you pack all your stuff in your backpack, and then you go out in the woods. And then if you didn't bring the little coffee mug, you just don't have a coffee mug. And so in this thing, if you don't build yourself a debugger, you just don't have a debugger. And maybe we should build a debugger. It's kind of useful.
Well, speaking of, I don't know that we're going to get to the debugger tonight. We may have to save that for another episode. But shall we head off to the Adam Barth code machine?
Yeah, let's do it.
Let's do it.
Okay. I got this fancy iTurn2 terminal set up, which
it's way fancier than my terminal.
We'll see how it works. So I got these 3 terminals here. Okay, so what have I done up to this point? So I went to fuchsia.dev, which is the website.
Yep.
And there's a getting started link, and that shows you how to download the code.
Mm-hmm.
So I've downloaded the code and I've compiled it.
Mm-hmm.
So I compiled a slightly different version than what the instructions on the website tell you to compile. So they tell you to compile a thing called Workstation, which actually has a UI and some they call terminal chic user experience. So I compiled something slightly different. I compiled core.
Okay.
So core is just the raw core of the operating system. And we're going to run it in a headless way today. And we're going to play around with the internals of it. Because core is way more, it's more of its guts exposed unless you play around with it more.
Are things more sealed in the workstation thingy?
Yeah, so the workstation has, a lot of the stuff we're going to show here is about on-demand software loading. So the workstation is set up with its pre-configured set of software that is the software that it's supposed to have. You can't just sort of add whatever you want to it. You sort of start with core, you add things to it, and that's how you make products out of things.
Okay. All right. So you went to fuchsia.dev, you downloaded the source code, which is, I presume, is quite a bit, and then you built it.
Took a little while, yeah.
And you're running it in an emulator of some form?
Yes. So this is the set command that I used instead of the workstation one.
And FX is the Fuchsia tool?
Yeah, FX is it's this multi-command tool that does everything that you want. It's like a shell script of Doom or whatever.
Okay.
So here in this background tab, I'm going to start running the emulator. So this is I'm telling the virtual device launcher to start, and I'm telling it to start headless.
Is it easy for you to embiggen the font just a little?
This font is just I can embiggen it a little bit. Yeah. I think if I shrink this down, it'll actually get bigger.
I see. So you're doing the FX command, and FDL is the Fuchsia device launcher. And then if you scroll back up.
I said I wanted headless.
I see. And you're starting the emulator, which is FEMU or something?
Yeah, there's both QEMU and FMU or something. I don't know. It just runs one of them.
But anyway, it's an emulator that Fuchsia knows how to run it, because Fuchsia probably doesn't have device drivers for whatever device, your MacBook or whatever.
Yeah, and this is all just the way that I use it at work, because I run it in the emulator, because if I'm working on the core of the system and I make it not boot, I'd rather it not booted in an emulator than not booted in hardware.
Yep.
And so then now it's running on localhost and it's listening on this port.
Okay.
So I'm just going to take that over here and I'm going to copy the whole thing actually.
And this is like when you run on the iOS emulator or the Android emulator for hacking on those things. They just run inside a box on your machine.
Okay, so now everything is all connected. So I'm going to run fx log here.
Okay.
So at the top, we're going to see log messages coming from this emulated system. And they're sort of going to scroll by, and then sometimes we'll see some interesting ones.
Okay.
And then over here, I'm going to say fx shell. So this $ prompt is now coming from inside the Fuchsia environment.
Wow.
So there's basically literally just SSH'd in to the device.
So like if you type uname or whatever the Fuchsia equivalent is, it'll say Fuchsia?
Zircon, yeah.
Okay. Because Zircon's the kernel?
Zircon is the kernel. Fuchsia is the whole system. So like analogy with Windows, like NT is the kernel, Windows is the whole system.
Okay.
So now I want to show something that I think is really neat. So over here, I just booted this thing up. I'm going to run ls. So what's interesting is not what happened in this window, but what happened in this window.
Okay.
So this, prior to me running ls, this system did not have ls on it. It just, in the time I hit enter, it discovered an implementation of ls and basically installed it on the device. And now I have ls. So it went and fetched this cryptographic identity for its ls. And now I have ls running on the device. And if I run it again,
sorry, go ahead.
Go ahead, ask your question.
Oh, sorry. That ID was baked into the system you built, or?
Not exactly. So if you look in the bin directory, there's tons and tons of things, but let's look at the entry in bin for ls.
Okay.
So like on sort of Unix or POSIX systems, there's this like hashbang thing, which normally like lets you run a shell script or something.
Yeah.
So on Fuchsia, there's hashbang resolve, and then you can give a URL.
Okay.
Which says when you run this program, instead of trying to, I don't have the executable here, instead go get the executable from this package at this path.
And is this like a real URL? If you typed it into a browser, it would like give you a JSON blob or something, or?
Not if you took it just a regular browser, it wouldn't, because it doesn't know this scheme. So you could actually change the scheme to be HTTP here, and then you could actually fetch software off of HTTP, and it would run and execute. So those URLs you could type. So this says, we're not using HTTP to go fetch this thing. We're using the Fuchsia package system. And so part of what I'm running back here is, in addition to running the emulator, I'm running this package server.
I see.
And so this, in my output directory, I have a whole package server, and it got a request for these blobs that it needed to run ls.
And there must be like a name server somewhere that resolved that name of ls into that cryptographic hash.
Yeah, so one of these JSON files had an entry that said, this package server knows about the package ls, and here is the cryptographic blob that, the name of the blob that contains it.
Okay. Cool.
So
that's wild. Like my Mac system does not like know how to pull ls, or my Windows system does not know how to pull ls from the internet.
Yeah, so one of the original ideas is the sort of idea is based on the idea of a web browser. So a web browser, you have this URL bar. You can type in URLs, and it will load up web pages that it's never seen before and show them to you. And so this system kind of answers the question of, what if we did that, but you could run just arbitrary software that way? And so to do that, you really have to think really carefully about security, because a web browser is really giving you a lot of security benefit, like it has a sandbox and everything. So that's why the system is very highly rotated on security, because it has the idea that you're just going to be fetching this software from the internet or from your package server, and you're going to be running it on this device. You really want to contain it and make sure it's secure.
Because like ls is all locked down when you run it, I assume.
Yeah, so we can look. Let's play around with ls a little bit, and then we'll look at some of the rest of it. So I want to show you some other neat thing you can do with this. So here in the source tree, I have the source code for ls. We get it from a open source project called Sbase, which has sort of like small implementations of like normal command line utilities.
Mm-hmm.
So let's just go into ls. This is the main of ls. I'm going to add a print statement here.
So hard to read this after reading weeks of Rust code.
Yeah, I mean, we probably should find like a Rust implementation of these like core utility functions.
Your quote. That's not going to compile.
Oh, did I mess it up?
Your new line was outside your quote. Yeah, C was going to have a bad time with that.
So I've just edited the file, and I'm going to build a project called publish. So what publish is going to do is it's going to compile that C file, package it all up, and put it in my package server.
Right, so we edited the Fuchsia's source for ls, and now you're running the fx command, which is the Fuchsia developer tool command, sort of like the Flutter command for Flutter. And you're running the build command, and you're building the publish step or the publish target.
Correct. So the publish target basically makes sure that all my packages are up to date, and they're published into my local package repository,
which then your package server knows how to serve.
Correct.
Yeah.
And now I go back over here. So here I'm SSH'd into the device, and I just run ls again, and now I'm running the new version of ls that I just wrote.
There we are. So does Fuchsia then, every time you type ls, it goes and tries to call out, or presumably in dev mode it does this?
Yeah. So this is the engineering configuration of the system. So in the engineering configuration, every time you resolve a package URL, it goes and pings your package server to basically revalidate the cache. In production configurations, these settings are set differently so that it knows that, okay, this thing is not actually going to be updated every time you run it.
And this is like a DNS cache in your browser, like a time to live, right?
Yeah, like when you run a web server in development mode, you turn off your caching because every time you want to edit something, you want the new version. Right? Yeah, so you can actually see that. So when I type ls, it says it resolved the symbolic name to this cryptographic hash.
Yep. Okay, cool.
So let me take that print statement out because it's going to be annoying if we're going to use ls to explore the system a little bit. I want to show you the internals of this package, so you can see what is in the ls package.
Because the ls package gets installed on the Fuchsia system somewhere, or cached, I presume.
It's more like a cache than an install. So in other operating systems, installation is a push mechanism, right? You like type apt-get install a thing, right? And then you got it. And if you want to get rid of it, you say uninstall the thing. So here, the idea is the entire universe of software is available to you at your fingertips. All you need to do is mention it. Then it'll come and run on your device. And when it's done, or you run out of space in your cache, it'll disappear and float away. And if you want it again, it'll come back when you need it. This is a concept of ephemeral software.
Okay.
So if we look in, there's a mount that we have access to here called packagefs, which contains, is like a file system presentation of all the packages on the system. If I go into the ls package, version 0, just kind of a weird thing. So this is what's in the ls package. So in the bin directory of the ls package, there's the ls binary. In the lib directory,
WD, so we can see the whole path here.
So here I'm inside the ls package. So it has the ls binary, and then in its lib directory, it has all of the shared libraries that ls depends on, including like libc++ and libc and a bunch of other funky ones like the logger and such.
Okay.
And so what this means is each piece of software in the device has its own copy of those libraries. So ls has its own version of libc that's potentially separate from every other piece of software on the device. And so if libc changes its ABI, then it's fine. ls has its copy of libc, cat has its own copy. They don't conflict, and you avoid DLL hell.
And you say potentially because I presume there's some sort of uniquing caching mechanism below these?
Yeah, so if I look in the meta directory, I can have the contents of the package. This says my ls binary is a blob with this cryptographic identity.
Okay.
And my dynamic loader is a blob with this cryptographic identity. And there's another mount here called blobs. This has all the blobs for the entire system in it. And so if two different programs have like identical bits for their dynamic loader, they'll share the same blob in the underlying blob store.
You end up caring a lot about blob size then, because you kind of want everything to be small.
Well, you care about blob reuse because you want as many packages as possible to arrive at the same blobs.
Yeah.
And so you do the duplication there. So like when ls maps libc into memory, if someone else has already mapped that blob into memory, then it's already there, and you can just share the pages.
Okay. Neat. Do you have more places you want to take us, or are we supposed to grow you now?
You asked about sandboxes. I wanted to show you a little bit about that. So,
So we're back on the host machine.
We're back on the host machine. This is a tool that lets me sort of reflect on the system. So what I've done is I've asked the system, please list for me all of the components that you have. So these are all of the components that make up the system.
You were using FX before, you're now using FFX.
Yeah, so, okay. So Fuchsia is in very active development. So FX is the future FX. So someday the future FX will come to replace the old FX. At the moment, we have both because we're awesome.
I just want to point out we do have we got Rafal, who likes reminds me of NixOS. I don't know that one.
Yeah, so NixOS has a similar idea where it tries to hermetically package software to get the same property of being able to add and remove software very easily from your system.
And then we have someone whose name I don't know how to read, and I don't speak the language, so I don't know if it's safe to click on. But you were telling us about the component list here.
Yes, I just wanted to show you like an example component. So let's show the HTTP client component.
And this is the thing that like does the fetching, or it's part of the system that does the fetching.
Yeah, so this is used to actually make HTTP connections. And so it's a v2 component. It's currently running in this job. It's been running for this long, etc. But what's interesting down here is this describes its sandbox. So this program, the HTTP client component, has only 5 incoming capabilities. So in its universe, when it looks out into the system, it can only see exactly these 5 things, and it can see nothing else about the system.
So like, go ahead, sorry.
So the 5 things it can see is it can see a log sync, so a place to send its log messages. It can look up names, so like do DNS resolutions, and it can open sockets. And it has access to its own package and its own configuration. And that's it, like literally nothing else.
So like it can't see the file system.
And this is its file system. It's basically a file system consists of a view of its own package, these 3 services, and its configuration.
So like it can't see any, like presumably there's a way to allocate memory that doesn't go through this, or like is there some like, how do I malloc if all I can see are these things?
Yeah, so it also gets, so not listed here, it gets what we call the VDSO, the virtual dynamic shared object, which allows it to issue syscalls. And one of the syscalls is create a memory object. And it also gets some other capabilities, like it gets a handle to its own process and a handle to its own address space so that it could map memory in its own address space and things like that.
And those are so common, they're not displayed in this tool.
Yeah, they're also sort of internal, like it's not, it can't, when you get a handle to your own address space, that doesn't let you influence anything else about the system. Yeah, so if I got a handle to somebody else's address space, it would show up in this list because it's incoming, it's coming into this component as opposed to inside.
And the bottom part is saying these are the services that it vends out to the system?
Yeah, so these are what it consumes, and this is what it produces. So it produces the HTTP loader service. So it exposes it from itself, and it allows other people to connect to it. So we can go look at.
I was just everything in the system is both a client and a server in this way.
Pretty much, yeah. So the whole system consists of we call a topology of these components, where these services are then routed from one component to another to basically wire them up. So there's some like places where this bottoms out. So like there's a capability which is all physical memory.
Sure.
So like your drivers eventually get some slice of physical memory to work with the hardware.
But those sort of like, sorry.
It's like turtles all the way down. Like it uses this structure all the way down to like physical memory.
And I presume nobody has those big mega capabilities, right? Other than the kernel.
Well, there's a thing called the driver manager, which we can see.
Does it have the all physical memory capability?
Yeah, it does. Its job is to load drivers. Where's driver manager? Here's driver manager. Its job is to load drivers, figure out what parts of physical memory and divide like registers and stuff those drivers need, carve off that piece and give them to that driver.
Okay. Huh.
And so like the file system host, for example, this is where the file systems live. So it gets access to like the whole disk. Like here's your disk controller. Like start like carving it up into partitions and block devices and file systems, and then ultimately exposes directories.
Does that mean you can end up with like multiple file system controllers on this thing? Like, because they're all peers, it seems like.
Yeah, like if you had a common thing that we do in testing is we just create a fake like partition that's backed by memory. And then you can instantiate a disk controller on top of that and build the whole storage stack. And then you have the whole in-memory storage stack that's really good for testing. In fact, this whole setup is really good for testing because you've enumerated all these incoming capabilities. They're all points for dependency injection.
Oh, totally.
When you want to test the HTTP client, you basically inject a fake socket provider.
Yeah.
And then you can test it to your heart's content.
Huh. That's cool. Okay. Do you have more on your tour, or is it question?
I just wanted to show what one of these protocols looks like, if that's.
Oh, okay. Please.
Because we're connected with all these different capabilities. Each of them is a protocol. I'm just going to give an example of a protocol. So the protocols are in the SDK directory, in the fiddle directory. This is a list of basically all of the protocols that the system uses, either to talk to itself or as an application, some of them you can access.
Can we PWD again?
Sure.
Just so we know.
We're just in the SDK fiddle directory.
Oh, okay. So we're on the host again.
We're on the host.
The fiddles as these are these directories or files?
These are directories. So if we go into like net HTTP client is an example of one of these files. So like here's the loader.
I see. So these are the protocols, presumably exposed by. You don't have fiddle files for things that you consume, do you?
Yeah, there's descriptions for all of these protocols. So like the log sync.
Oh, sorry. Go ahead.
Like the log sync protocol has another file like this that says, "Here's how you produce log messages."
That's so cool. We had a couple more comments. We had Rafael was saying hot restart for drivers.
Yeah, pretty much. You have to be a little careful to actually shut down your driver in a way that doesn't mess up. Like if you leave the DMA transactions going, they'll just like start spamming over memory. So you kind of have to shut down your DMA transfers, then restart your driver, then turn them back on. But aside from that, yes.
And Chris Sell says, does it run Flutter?
It does run Flutter. I actually have I want to show something about that. If we switch to I'm going to turn the screen share off and turn on a different screen share.
Okay.
Dun, dun, dun.
We're so big. We can get bigger.
So you can project it. I put it up there.
Oh.
So this was the first time we ran Flutter on Fuchsia.
You mean
so
like
this was actually
6 years ago or something?
Yeah. So this was in September of 2016. So what this is this is a screenshot of QEMU,
Uh-huh.
and we had hacked the system so that the place where the virtual console showed up, we had plugged that into Flutter, so Flutter could use software rendering to draw over the virtual console, and so we got the like text and like the Flutter gallery running at that stage.
Yeah, the Flutter gallery looks a little different now. I look at it and it looked normal, and then I was realizing, oh no, that was like a 5 years ago Flutter gallery.
Yeah, so basically the way we built the system is a little funny. So we had a version of the system running on top of Linux, and then at some point we decided that the Linux part wasn't helping us, and we wanted to redo the lower part. So we redid the lower part, built this kernel that could run like very basic user space programs like Fortune and things like that. And then we went immediately from there to running Flutter. And so we had to port like ICU and Skia and all of Flutter's dependencies in this like mad dash to basically get this screenshot of like being able to render like text and graphics on the system.
Yeah, you didn't quite have, I think those were like emojis or whatever, like custom fonts or whatever yet. But
yeah, you can see like up here, we just could not handle emojis. We were not there on the first day.
Files or whatever, yeah. Cool. Should we go back to the tour?
Sure, or we could do questions if you want to do questions. Or
I don't have any live questions yet, other than the ones I've shown you. But it looks like you have some queued up.
Yeah, so these are questions people sent over Twitter.
Okay.
So this question is, wants an explanation of Scenic, Flatland, and Flutter, and if Flutter can work as a compositor. So Scenic is a component, just like the HTTP client component that we saw, but its responsibility is for graphics. So it gets handed a capability, which is the entire screen. And like the file system is supposed to divide up the entire disk into directories and files, it divides up the screen into what it calls views. And so the views form a hierarchy, just like a directory system. And then each view can be populated by a different component. And so Flutter, for example, can populate a view, and then views can have subviews. So Flutter running on Fuchsia can have subviews that then can be populated by other components. And so can Flutter work as a compositor? Not quite, because Scenic is the compositor, but it could work as a window manager, for example. So if you build the workstation product, then the window manager there is actually implemented in Flutter, and then it runs, for example, a simple browser and a terminal as a child window. So it's not actually doing the compositing, it's doing the window management. So it's telling Scenic how it wants these things composited.
Mm-hmm. I mean, Flutter at its base layer knows nothing about Fuchsia. There's like an adapter, basically, that adapts between Flutter world and Fuchsia world.
Yeah, we built some widgets. Like there's a widget called Child View that knows how to go connect out to Scenic and tell it that it wants a child view at a certain place. And then Flatland, just to answer that part of the question, just like there's FX and FFX, we originally built the system with this three-dimensional compositor, and it turned out that our customers wanted two-dimensional compositing. And if you simplify down to 2 dimensions, you can do things faster. So Flatland is the new two-dimensional compositing universe.
Yeah, I remember, because the Flutter even, I think, still exposes some of this in our API. Like there's a depth parameter on the material object. Which
we had this dream. So material design is supposed to be this like physically modeled idea where like different buttons have elevations or something. And so we, for whatever reason, we decided to actually try to physically model the material objects. And so an elevated button would literally, in 3-dimensional space, be elevated by 2 units above the thing. And there's actually a mode you could do in the system where you could like go off axis by 45 degrees and you could see the like floating buttons. Mm-hmm. But it turns out to not actually quite be true. If you try to actually physically model all this stuff, things like run into each other, and like it doesn't quite actually work. It's more of a stage play than a reality, I'd say.
Yeah. It's funny, this came up actually again this week in Flutterland, because we were fixing the shadows. Because Flutter, we use some fancy shadow stuff down in Skia, and we like have a light source that like projects down and like makes the shadows. I mean, you wired up this code, so you know this, but like, but it had like a fixed offset from the like top left corner. And when you make a really big window in Flutter, which you could do,
the shadows get cast really long.
Yeah, it kind of looks 3D in a sense, in that like your lower right-hand shadows are really big.
That's cool.
But we had to fix it. Cool. Simon asks,
yeah, I'd like to hear your viewpoint on what makes Zircon different, special from other kernels. So people always like characterize these systems by the ways that they're extreme. So people ask a question like is Zircon a microkernel? So I think not really, because it has like 100 syscalls, and your traditional microkernel has like 4. Like its goal is not to be minimal. It's just like a practical thing that's there to solve our problems. But one thing that makes it extreme is there are no syscalls that take strings as inputs. So like in
strings.
So like in Windows, there's a function called create file, where you pass in a path for a file. Mm-hmm. Or in Linux, there's a function called open, where also you pass in a path. And there's nothing like that in Zircon. Like you always, it deals entirely in numbers. It doesn't know anything about strings.
Huh. And is that strings avoid Unicode or?
Well, it's really has to do with the fact that it's a capability-based system. So you can only operate on capabilities, and like a capability is just a number, like a 32-bit number. Mm-hmm. And so whenever you have a string, that tends to be used to address, like to name something. Mm-hmm. So when you open a file, you say, I want etsy/password, right? Sure. And that says, kernel, please let me see the password file. Mm-hmm. And so if you take away all the strings, you lose the ability to name things. So you can never ask for the password file. You can only get the things that you have. So we have the ability to ask for things, but it's outside of the kernel. It's up one level.
Yeah. It's fascinating.
Another thing is like the kernel has no notion of user. So in Windows, there's a very elaborate access control system where every object is associated with a security identifier and an access control list, and there's a thing. Linux, every process has a user ID and a group ID, and the kernel makes lots of like checks against that. Zircon just has none of that. It has no concept of user whatsoever.
Huh.
The way it does access checks is just, do you have a handle to this thing? If so, great. If not, no way.
No, I don't have a sense for kernels. Is like 100 a lot or a few? Like how many syscalls does Linux have?
Linux has I think about 300.
Okay.
But it's a little misleading because Linux has a syscall called IO control or ioctl. Mm-hmm. And so that's a syscall that takes as the first parameter another 32-bit identifier for what you want to do. And so there's like a huge universe of functionality that's just behind ioctl. And so counting syscalls is sort of like not a super sensible thing. And we have some of those things in too. So like we have there's a syscall that operates on a VMO and takes the first argument is what op do you want to do? And there are like a dozen ops that you can put in.
I presume that like you can't live hack on the kernel. You have to reboot the device, presumably reboot the emulator, but you can on much of the rest of the system.
That's right. Yeah, so I can show you that in the other window if you want to flip back to it.
Sure.
Maybe we should go through the questions first. And then
yeah, we got a few questions. We should. I keep looking away to check to see if anybody else is asking others.
Yeah, so besides security, what are some other strong points of Fuchsia? So I think updatability is like a huge strong point. And it's sort of what I try to highlight in the first part, is because the system is built out of these hermetic packages that run in these little self-contained sandboxes, you can add and remove things from the system very easily and keep it up to date very easily. So there isn't a lot of coupling between the different parts of the system to cause them to have to be either updated at the same time or like have a lot of coordination between them.
Go ahead, please.
I was going to say an example of that is the drivers. So the drivers work just in the same way that HTTP client works. They have some set of protocols that they speak, and those protocols are binary stable, which means we can take drivers and we can update the whole system around it and leave that binary driver exactly as is, just like if it were like an application.
But yeah, you have this updatability, and you address some with the driver level that like there's some sort of stable binary ABI or something for the drivers. But what about like all the fiddles presumably you have this explosion of like fiddle protocols and versioning they're in.
Yeah, so the fiddle protocols are designed, like a lot of the careful design work in fiddle is around the wire format. So when you send a message to another process, you format it and you send it over a channel, which sort of feels like sending it over the network. And so the structure of the wire format is designed to be extensible and evolvable over time. So you can
have somebody who wants to talk new fiddle to something that talks old fiddle, like a version of I don't know what file system driver. Cool.
Yeah, it's sort of like it's a lot like Objective-C in a sense. So in Objective-C on Mac before Swift, when you could send messages to Obj-C objects, and then they could either tell you, hey, I don't know what that method is. Can you try a different one? Or they didn't leak a lot of their internal structure. They didn't have what they used to call a fragile ABI in the Obj-C world. So we do that same thing, but instead of sending the message within a process to like a shared library, we send it across processes to another component.
Yeah, because it's interesting because Fuchsia has this internalization of its linked dependencies. But then, like, you don't want to end up with multiple Windows servers running. Like, if somebody knows the old Windows Server protocol and the new Windows Server protocol, you need to have some way to either have a stable protocol or
an adapter. So, for example, we have a Wayland adapter, so we can run software that knows how to speak to Wayland. But it's not like we have a separate Wayland server running. That thing just knows how to tell Scenic what the thing wanted to do in Wayland.
And does that Wayland adapter run separate from Scenic?
Yeah, so it's just like you sort of imagine it like a service-oriented architecture. So it on one end it exposes Wayland, and then on the other end it just talks to Scenic, just like any other client talks to Scenic.
Well, you could imagine with that you could end up with Wayland, like a Wayland 1 adapter and a Wayland 2. I know nothing about Wayland, or the Wayland versions at least, running in parallel for talking to different things.
We've actually done this with the network stack. So we're currently on the second generation of the network stack. We had a previous network stack that was built on LWIP, and we're actually working on a third version of the network stack, which is written in Rust. And we just swap it out and just like keep the protocols the same. And none of the clients know, and we can run them both in parallel, talking to different NICs or even like talking to the same NIC. And like you just route one socket provider to one thing and another socket provider to another thing, and it all just works. Like,
you were not kidding about the active development part. If you have 3 network stacks.
No. The first network stack is that one has been gone for a while. We just have 2 right now. But we have one that works, that is okay, and one that we think is really cool that doesn't work yet.
What do we got next?
Talk about stuff where Fuchsia is not as good as other systems. So I think that's a really important question. So a lot of operating systems have a lot of work put into them, like huge numbers of years by huge numbers of people. And so it's sort of fun to show off, here's the neat, shiny thing. But it's really important to be respectful of the fact that other systems are a lot more mature. So as an example, currently our immutable file system. So everything we've done today so far has been with our immutable, cryptographically verified blob file system. We also have a mutable file system that way you can create files and read and write them like you would expect. So as an example, that file system today, when you read the first byte of the file, it reads the entire file off of disk and puts it in memory. It doesn't know how to access a sparse file off of disk. And it's because that works. It's not great. Like, it's not great for performance, not great for memory usage, but it's allowed us to get other things working. And it turns out we don't use the mutable file system a ton. And so its limitation isn't holding us back too much, but like, it's clearly something that we're going to have to change and improve. And there's a lot of that. Like the LS thing that I showed you is from Essbase. It's a pretty simple LS. It does what it does, but it's not as fully featured as GNU LS for sure.
Yeah, I mean, some of this is also just principles of good software development, right? Like, you build the things as you need them because the needs change. And so, like, I think it's actually, my understanding is that Fuchsia is shipping on these home hubs, right? And like, if that's where you are, you don't need to run VI on a home hub, or whatever. So you may not need a lot in terms of a mutable file system. And so it
So
sounds
like another example is like multi-monitor. Like that device just has one monitor glued onto it.
Yeah.
And so our system is, has the idea that maybe someday it'll have multi-monitor, but like if you tried to plug in a monitor to its USB port, like it wouldn't really work. Like,
yeah.
But that's part of just being in development, and you have to sort of solve these problems as you go. And that's why one of the things that was really good about the Home Hub is we had very clear performance targets that we wanted to hit. We wanted to be as fast as the old system in every measurable way possible, and we spent a lot of time doing that. And like it was a lot of work, and it's made the system like good in those ways. And for use cases that were not exercised in that device, we're sometimes 10 or 100 times slower than other systems. But we'll get there, and we'll work on them, and we'll make them faster. And
I mean, there's a cost to all this too. Like as you build up, pieces of your system and pieces of your organization, there's this like calcifying effect. Like once you build a thing, you have to drag it with you. And so like, again, you and I worked on projects together for a long time. It is really healthy. Like Flutter is another example. Like we don't support multiple windows. I know there's some patches in flight to do that, but like that's because your Android phone does not have multiple windows.
Yeah, and you see some of that in the system. Like we've built a bunch of things early on that we thought were going to be important or useful that haven't turned out to be so useful, and so they kind of live on as strange little vestibules in this like elaborate building. Some of them we go and trim. Like, okay, we really don't need that. Let's rip that out. Some of them we leave, just because they're not harming anything. So like we have a PTY system that's sort of kind of half built, doesn't quite do pseudo terminal stuff, but like it's if you really wanted to have like a multi-user system where many people could log in with SSH at the same time,
sure,
you would probably need a fancier PTY system than what we have.
Yeah, but the Home Hub doesn't have that.
Yeah, and like when we need it, we'll add it, and like that's kind of how it's like this how it goes. Fiddle internals and how portable it might be to other platforms. So fiddle internals is like that's a whole show we could do about that. But I was trying to give this short answer. The first level answer is Fiddle stands for Fuchsia Interface Definition Language. It has a bunch of Fuchsia concepts built into it. Like it has a notion of a handle built into it. So it's pretty specialized to what Fuchsia is doing. That said, if you take the handle part out or abstract it a little bit, then it actually makes perfect sense to run on other systems. And the other thing is, remember when I ran the ffx component list, ffx show whatever commands? Mm-hmm. Those are actually running on the host side, and they're actually using Fiddle. So they communicate with the device over UDP or TCP, I forget which one it uses. And then it's basically sending Fiddle messages back and forth over that network protocol. And there's a little library inside that binary that emulates the enough of the Zircon kernel primitives that we actually just write the same code that we run on Fuchsia on top of Linux, and it runs against those things. And then on the other end, it holds the real Zircon objects and then proxies the operations back and forth.
So let me play that back to you, make sure I understand. You're saying you write what is effectively Fuchsia code, and you compile it on top of this shim fiddle thing that knows how to remote its fiddle commands over a pipe of some form over to the device to a real Fuchsia kernel.
Correct. So the thing is called overnet if you want to dig in the code and look at it. It basically allows you to speak these, have channels and sockets and stuff, but have them go across from a Linux host or a Mac host in this case over to a Fuchsia target device.
That's crazy.
Well, you build up all this technology to talk and communicate with things.
Sure.
And then you want to tool it over from the host. Early on in the system, we used to just like SSH and like run shell commands to go do things. And it's like, you're having to build all these like weird shell bridges. And so at some point we just built a generalized bridge for Fuchsia, for Fiddle, and then we could interact with the whole system.
Well, as you alluded to, it probably would be a whole show on Fiddle. And I don't think this is the last Fuchsia show we will ever do. I think we have some plans for the next few shows that won't be Fuchsia. But I think this is definitely a topic that would be fun to revisit and go deeper into parts of.
We had a live question in the chat if you want to project.
Oh, yeah. Sorry. Rafal, how hard is it to port existing Fuchsia CLI program? Existing Linux CLI programs to Fuchsia, assuming they're written in C or Rust?
Yeah, so the good rule of thumb is if the program knows how to run both on Linux and on Windows, then porting it to Fuchsia is relatively easy.
Okay.
If it only knows how to run on Linux, then depending on what it's doing, it can be a little tricky. So we have a compatibility layer we call POSIX Lite, which contains the parts of POSIX that we think don't negatively impact security, and then we provide that interface on top of the underlying Fuchsia primitives. But for example, some command line, like in SBase, for example, there's an xargs program. And what xargs does is it forks a bunch of child programs to do the thing that you asked it. And so fork is not a primitive that we have because fork has an implicit capability transfer. If you have a bunch of open file descriptors and you fork, then implicitly those get transferred to the child. And so we would much rather that all capability transfer in the system was explicit. And so we have a process creation API that's a lot more like Windows, where in Windows you call create process, and then you start giving it the things that it needs. And so like for SBase, most of the stuff in SBase just compiled without us touching it. For some of them, we had to add a few different changes to it to either work around things that we don't have in POSIX Lite or tweak a couple things.
So what I heard you say was that if your thing uses a small amount of POSIX or enough that it fits under POSIX Lite, it might just straight up compile on Fuchsia.
Oh yeah.
Huh. That's cool.
And then if you have a more complicated program and it runs both on Windows and on Linux, you probably have a platform abstraction in there somewhere because like process creation is different on Windows and Linux. And then you just sort of plug in a Fuchsia thing into that, and it usually
you mix and match a little bit of your Windows and a little bit of your Linux.
Yep, and it gets you sort of there. I mean, it still worked. Like, don't get me wrong, but it's you generally don't have to like redesign or re-architect the software. You're just sort of like filling in the right platform abstractions.
Okay. Shall we get through the last few questions? I think we're getting towards the end of the show.
More about the ideas on user space. So fundamentally different. I imagine porting over existing software is far from trivial. This is sort of a similar question. So when you port over software, it ends up being different than the software you would write if you were just designing it for Fuchsia. Like you end up with much bigger components that are do a lot more things, whereas the natural way to write things for Fuchsia is you write a lot of little tiny components, like the HTTP client component that all it does is know how to like translate HTTP to sockets, right?
Yeah.
But the compatibility layers are like super important because there's like many years of software development, and if you had to throw all that away and start again, you would never get off the ground with your new operating system. So would your guess
be that the various programs we've written here on RDE would just run on top of Fuchsia because they just use Rust and a little printf?
I think so. Like I think the parts that have to change. Like remember we did the sound analyzer project, and we had to read the file, and we had to like mess around with like Mac's sandboxing config to get it to be able to, like that's exactly the point at which it would probably be different on Fuchsia because you would get the audio file from a different place. But once you had it open, then the rest of it would just be the same basically.
Okay.
Will I ever be able to use Fuchsia as a Linux replacement or in a general purpose desktop? What about a server? I don't know.
Future.
Yeah, I mean, ever's a long time. Certainly, it's not there today. Like, if you look at the workstation product you can build, we have a thing called Simple Browser, which, the web view part of it is pretty good because the Home Hub has a web view, and so we had to get that part working. But the browser part of it is pretty basic. Like, it has a URL bar you can type in, but I think it has tabs. But like, I don't know, the tabs are square, and I don't know, it doesn't have a lot of features.
It's not a.
But I also think it's important to realize that people always want to look at these things in a zero-sum fixed way. Like, is this going to replace X? Like, is this going to replace Linux on the desktop or whatever? And I think of it more in a there's like more to be had, right? If you have a system that's different than Linux, is maybe different for other things.
Mm-hmm.
And maybe there's new things that you could do with it that are either difficult to do with Linux or awkward, or you might benefit from a different application. And so, yeah, I think it's more useful to think about like what are the new things that you can do with this that are possibly additive as opposed to replaceative.
I also just look at the software world as it is, and it's only getting bigger. Like there's only a few tens of millions of developers, out there. And like that's just not the end state.
Or even devices, right? Like devices keep getting smaller and cheaper. And like that means, average person is going to interact with more and more of them. And that means the amount of attention that they have to like administrate each device is less. And so the system that has much lower administration, more easily updatable, like more secure, like that is a better fit for those kinds of products.
Yeah. We got a comment from returning viewer Nash. Porting a previous application to Fuchsia sounds like an interesting episode idea. I agree. Maybe we'll try that one of these days. So, cool. Well, I think we got a couple more minutes of the episode. Were there other things you wanted to cover? Should we put on our party hats?
We can put on our party hats, sure. We promised a live code.
Launch here.
We promised a live code a component, so we could try to knock that out in the last 9 minutes.
We could probably do that. Yeah, I don't know the party hat. My hat is just so gigantic. I don't think the party hat really fits.
I broke the string.
Oh, you broke the string.
Hat. So it's a little bit unstable on my head. I think it's going to fall off.
Also a bearer of a gigantic head. But at least we can celebrate.
I put the terminal back on the screen share if you want to put it back.
Oh, yeah, sorry. I fell down on my editor duties here.
Okay. I did slightly cook this in my other Easy Bake Oven. So we do have a chance. So I'm just going to make a directory in the source directory for RDE. And go in here. So the fx command can do everything known to humans. And so I'm just going to tell it to please create a component for me. So it's just going to create the source code for the component.
So we're on the host using the fx command, which is like Flutter, but Flutter create or fx create here. Okay.
So it just created some source code for me here. Well, it's just like spewing out a template, right?
Spewing out 2 files. And this is on our Mac host. We created a Rust template project for Fuchsia.
Yeah. So this file here in the meta directory is the manifest for the component.
Okay.
So this basically says I'm going to run a program that's an ELF binary. My binary is named this, and if I want to use any capabilities, I'll put them here, and if I want to expose them, I can declare that. And then I also include some common things like I want to be able to log, and I want people to be able to inspect me. So this is like your sandbox.
Wow. Use the built-in ELF runner to run native binaries.
Yeah. So you can run lots of different kinds of things. So your program is a very general thing, like a component, like a Flutter application is a component, and then you would say runner Flutter.
Okay.
And or you could have like a web page could be a component. It'd be like runner, browser or whatever. That's a whole yeah.
In the spirit of the evening, we're using our Fuchsia classes.
Yes. Okay. So that was. What's the manifest? Let's go look at the build files very quickly. So the build file says, here's my Rust binary. I want to make unit tests.
Hi, Manan.
Hello. I depend on all these things. Here's my source code. I want to make that into a Fuchsia component. I'm going to put that in a Fuchsia package.
And this is a GN file?
Yeah, this is our weird internal build system. If you use the
Chrome build system.
Yeah, we got it from Chrome. We got a lot of things from Chrome. If you use the SDK, we support normal build systems like Bazel and stuff.
Oh, but GN's great.
Anyway, so here's our Rust template that it filled out. I don't know, this stuff doesn't super matter, but
quite a bit of code.
Log info
async function main. Whoa, anyhow is just built into how Fuchsia rolls, or just how
how the template is. The template uses anyhow. I can go through this very briefly. So we run tons and tons of async code, because mostly what a program is doing is it's receiving messages from its clients, messing around with a little bit, and then sending messages to other services. It's just like a
They're all
little servers. And so we tend to run single or multi-threaded Rust programs that are then async awaiting all the time to send and receive messages.
Makes sense.
So each component runs a little file system to expose its services. So this is our like toy internal file system. And then you can register services in that file system, and they appear in your outgoing directory.
And by file system, you don't mean like something on disk. You just mean like a tree structure.
It is literally the same protocols that the on-disk file systems use. So like you can go in and ls and cat and inspect all of the components. That way they all get mounted in different places in the system.
And that we need to do.
Okay, we can do that.
Well, we can get a little demo. I mean, we're going to run out of time. There clearly needs to be another Fuchsia episode, but.
So I just added this hello RDE print statement, block statement. Let's see what I need to do. I need to add a dependency on the logging library because we already added the log statement. I don't really have.
This is in our GN depths.
Yeah. I just wanted to log
some baking in your Easy Bake Oven here.
I did. Okay. Then I need to go into. I'm going to add this to the universe of packages that exist. It's going to regenerate all my build files.
Args is like some part of the Fuchsia system here.
So these are the inputs to the build system. So I created this new thing. I need to tell the build system it exists. So normally you just attach it to the build graph, but because we're just going to do this as a one-off, I just added it as, hey, by the way, in addition to all the normal things you know about, also over here, there's this funny component that we just invented.
So don't view this little 5-minute hack and slash of a new component as like the correct way to add a new component to Fuchsia.
No, this is just like, let's do it in 5 minutes and make it go fast.
Yeah, makes sense.
Mostly spending the time generating the build system. At work, I have this really powerful computer that does this all really quickly. Like it made 140,000 targets. So there's a lot of stuff.
Oh, I see, because we edited some deep dependency in the build system. We hacked our way into some deep dependency in GN. And so we had to rejigger all the build files. Because that's GN's job, is to generate the Ninja files, which is the actual make files, basically. Yeah. And I know we're not gonna build 143,000 or 140,000 targets, are we?
No, it's smart enough to know that most of them are already built, and so we're running the same publish step that we did before, which will basically compile all of the make sure all of the packages are built and then include it in the package server.
Okay. And so this is going to build, and then it'll just vend it, and then do we have to install it, or do we have to like?
Nope, we just run it. There's no install step. Once it exists in the universe and it's compiled, you can just run it, even though this is. So the emulator's been running this whole time. We haven't touched it, and we're just going to be able to run it. I
see, because the package server will just, or the package server on your host machine will just vend it as a known like URL. Right.
When I tell the system, please run this component, it'll try to resolve that package into blobs, and the package server will know about it, and so it will succeed.
The way you hacked it in, did that like auto-generate a like bin / thing, or are we just going to run it more directly in some way?
No, we're gonna run it directly with a lower level part of the system.
Okay.
Assuming it ever builds.
While it's building, can we like see one of these running components, or maybe we'll see ours?
Yeah, remember when we did the component list? Those are all the running components.
I see. But you said we could like dive into the one through like the build system somehow. Or maybe that's another episode.
Oh, yeah, we could do that. So let's see.
Because here we're back on the device.
So now we're back on the device side. So there's a thing called the hub, which shows you all of the stuff. All of the What am I in? Oh, I'm in the sysrom.
Do PWD want to tell you?
These are all the components that exist here. So let's go look at the netstack component.
And so these are like running programs that because they vend their components as though it was a file system and they use the same protocol, you can just like ls. Ls is like turning into fiddle commands that they're intercepting instead of the file system.
Let's look at our PWD. So we're inside this place where we've mounted all of the components as their little file systems in our running system. Yeah. And so we're looking at the net configure. That's not what I wanted. I wanted net stack. So now I'm looking at this. It's like the proc file system. Yeah. So if I look at like out, this file system here, this is actually being served by the network stack. Now I'm inside the network stack's file system, and I can look at its services. These are the services that the network stack exposes. They just literally exist as files in this directory.
That's so wild. It's a little bit like Flutter is like widgets all the way down. You're just like, yeah, sure, we'll do file systems all the way down. It's a whole other userland file system.
Yeah, but unlike Plan 9, where everything is a file, here we have directories and stuff, but there's a really heterogeneous set of things that can exist in directories. Okay, so I built all this stuff, and now I should be able to say, in my Easy Bake Oven, I will run this command. So I've asked the component to run this new package that we've created. And so it created an instance of that component.
Oh, I see. The host told it to run it.
Yep. And then over here, we can see that in the FFX laboratory, our component made its log message.
All right. Clearly something we could dive deeper into.
But yeah, we sort of speed run it here at the end of the show.
Yeah, I mean, we're over time. So anyways, this was great.
I had fun. I hope the rest of you had fun.
I mean, we got all sorts of comments from folks, so I think it seems like the YouTubes also enjoyed. So to wrap up, we will not be doing Fuchsia next week. We're having a special guest.
Ooh, guest, exciting!
Yeah, I'm going to teach us some cloud stuff, is what I heard. And then I think we're going to do a guest after that, and then maybe we can line up another Fuchsia show if folks are interested. But as always, please send us your thoughts, love letters, hate mail, maybe not hate mail, to Rubber Duck Engineering. That's where we got a lot of these questions tonight, was the folks tweeted at us. And otherwise, you can do all that we did tonight, because this was all open source, right?
Yep. Every single thing is start there, getting started. You can do it all yourself.
Cool. Anyway, well, this is fantastic.
Thanks for joining us, and come back to the Fuchsia.
We get all sorts of swag. It was good to see you, Adam.
Yeah, see you next week.